start. Okay. So it's a pleasure to have today with us for our Tuesday seminar, Giada Casali. Giada is a postdoc at DIFA, working with Andrea Emilio, and she got her PhD in Florence in 2021. Research field is in galactic archaeology, mainly using data from Gaia and large spectroscopic surveys. She's expert in stellar spectroscopy and determination of stellar ages based on chemical clocks. And today she will present a talk with the title Galactic Archaeology Using Chemical Clocks. Please, Giada.
Thanks, the organizer, for giving me the opportunity to present my work. So in this talk, I talk about this additional tool to infer age for a sample of stars using chemical clocks. First of all, a brief introduction about what galactic archaeology is. So galactic archaeology is a branch of astrophysics that study the history of the Milky Way, starting from its resolved stellar populations. In that case, stars act as fossils, preserving the chemical composition of their parent gas clouds. And thanks to the data collected by Gaia and large spectroscopy surveys, we are able to map the Milky Way, so the structure of the Milky Way, its dynamical and chemical distribution. And then we are also able to have a map, so a three-dimensional chemodynamical map for more than 10 to 5, 10 to 6 stars. In this multi-dimensional space, actually, so we have a missing variable. This missing variable is the time, so the stellar age. And then these additional parameters is really important if we want to disentangle the different epochs of the star formation in the Milky Way and reconstruct its assembly history. However, estimating stellar age is one of the most difficult tasks of astrophysics because it cannot be directly measured like other stellar parameters such as temperature, for example. And for the reason we need to compare our data sample with so the observational data sample with the theoretical models. Here we have a list of different methods to infer stellar age. So the most commonly used technique is autoconfitting. These methods is really useful if we have star clusters, because in that case we have a lot of stars, rival chemical homogeneous stars along the entire evolutionary sequence. But its work so is not the best method if we have individual stars, in particular in the red giant branch, for example. Then we have other methods like astroseismology, lithium depletion boundary, kinematic age, geochronology, stellar activity, and chemical clocks. So in this talk, we focus on chemical clocks. Chemical clocks are chemical abundances ratio between two elements that display a opposite trend with time. So here we have an example. They are composed in particular with an S process element and alpha element. The S process element shows an increasing trend with time due to the latest contribution of AGB stars with a short time scale. The alpha element show an opposite trend with time due to the early contribution of supernovae type 2 with a shorter time scale, and the combination of them give us a steeper trend. So in that case, we can maximize the correlation with age. Here we have an example. So for this abundances ratio, calibrated on stars with well-known ages, allows us to derive age for a large sample of stars. So in sense, we have a sample of calibrated stars. We get for them empirical relation, and we can apply this empirical relation to a huge sample of field stars for which we don't know ages with other methods. Okay, so just to think about the application of these chemical clocks. So when we work with the chemical clocks, we need to take into account two important things. The first one is these chemical abundances ratios depend on metallicity. So as we can see from the left panel, we have different relation at different bins of metallicity. And then we need also to take into account the dependence of the position in the galactic disk, because relation in the inner region of the galactic disk are different from relation in the outer disk or in the solar neighborhood. So we can say we have three different groups of calibrators, so stars with well-known ages. And then they are solar twins. So solar twins are stars with atmospheric parameters, so temperature and log G, very similar to those of Sun. And for the reason we can have high precision spectroscopy, and as a consequence also high precision in stellar age. Then we, as I said before, star clusters using the isochrone fitting, and finally we have also stars with astroseismic age. So for the first subgroup, so solar twins, there are several works about solar twins and chemical clocks for these stars, starting from Nissen et al. 2015. This is a work about a larger sample of solar twins, more or less more than 500 stars with a high resolution and high signal to noise ratio. These stars are located in the local volume, and for all of these stars we have this list of elements. So in blue, alpha elements, in red, the S process elements, and we combine these different S and alpha elements to get 10 chemical clocks. And for each of them, we performed a multivariate linear regression, taking into account the dependence of metallicity, where is quite evident from this video. Here we have just two examples for yttrium over magnesium, yttrium over aluminium. And after, we also, to validate our relations, we applied them to a sample of field stars. Here we have an example. These stars are stars present in the Gaia HISO survey in the solar neighborhood. And these stars are color-coded by ages from yttrium over magnesium. There is a clear dichotomy between the thin and thick disk. So the thick disk is older than thin one. Then we also have a gradient in the thin disk. In particular, so the stars with high magnesium are older than stars with a lower magnesium content. And this dichotomy shows a different star formation history between the two disks. For the second family of calibrators, we have open clusters. This is a recent work by Vizcasillas. In this work, we analyzed 62 open clusters present in the Gaia HISO survey. In that case, we are not just in the local volume, but we have a large range in galactocentric radii, from inner disk for kiloparsecs to 20 kiloparsecs. Just a couple of slides about S process elements. So these elements versus metallicity shows banana shape. So there is a peak around minus 0.2 depth in phi over h, and the clusters are color coded. We have 3 different pins in galactocentric radii. The pink one are the open cluster in the outer region, and we can see clusters in the outer region are more metal poor than cluster in solar neighborhood and the inner region. And then they have also a higher content in these alpha elements with S process elements with respect to clusters in the inner or solar neighborhood. If we see the same plot versus age, we have this trend. So for all of them, and in each beams in galactocentric radii, we have a increasing trend with time. In particular, if we see at a given age open cluster in the outer region have higher content in S process elements with respect to stars clusters in the other region of the galactic disk. So and more or less we see the same if we study chemical clocks. So the combination between these S process elements and alpha elements. Here we have just 2 examples: yttrium over magnesium and barium over magnesium. So for the 3 beams in galactocentric radii, we perform a multivariate linear regression, as we can see from this equation. And we see open cluster in the outer regions have a steeper relation with age with respect to the other 2 beams. But the problem of the problem of open clusters is the limitation in age. So we don't have open clusters with age larger than 7 giga-year, more or less. And in this case, stars with age from astroseismology can be helpful. Also, in that case, we apply this relation to to a sample of field stars present in the Gaia ISO survey. We see alpha over iron versus metallicity in the 3 beams of galactocentric radii. Also, in that case, we see stars with higher alpha over iron content are older than stars with a lower alpha over iron content. And this depends on the star formation history. Finally, we have also stars with astroseismic age. Just a brief introduction about astroseismology. So astroseismology is the study of stellar pulsations related to the physical properties of a star. So we can detect this oscillation by measuring the change in brightness of the star versus age versus the time, sorry. And performing a Fourier transform, we can get power spectrum. From the power spectrum of a star, we can get age using two different approaches. The first one is using average seismic parameters, so the so-called nu max and delta nu, and using the equation, so the scaling relation in the right part of the slide, we can get age, log G, and distance. The second method is based on individual mode frequency.
Sorry, what is log G?
Sorry, log G is the surface gravity. Log logarithm. Sorry, maybe because I'm still sorry. So, and the second method is based on individual mode frequencies. In that case, we have more constraint than just 2. And in that case, we can get more precise ages. And I just highlight a paper using this method, where they found uncertainties around 11% in age distribution. So in this work, we are analyzing 3 different samples of stars with astroseismic age, that is K2, Kepler, and TESS. And we cross-matched this sample with Gaia and Apogee spectroscopy survey. From on the right side of the slide, we have the map where of the different campaigns of K2, Kepler, and TESS. And for all of them, we computed ages using the Param tool. Here we can see the uncertainties on ages. And for Apogee, we have just one S process element, cerium, because the lines of S process elements are in particular in the visible part of the spectrum and not in the infrared part. And Apogee observed just the infrared part of the spectrum of stars. Here we have the same plot that we saw for the open clusters. So the S process element, in that case, cerium versus metallicity for the 3 data samples. And in all of them, we see the same banana shape with a peak around minus 0.2. And there is also a clear gradient in age. So stars, the youngest stars have a higher content in cerium over iron with respect to the oldest one. And in here we have stars present so in the low alpha and high alpha sequence. So more or less the thin and thick disk stars. Here we see the same plot but versus age, and we remove stars in the high alpha sequence. So we take just if we see the small plot on the right side, we take just the red stars, so the low alpha sequence. And in that case, we see stars with higher content in metallicity have a lower content in cerium, and we have an increasing trend, in particular in the young part, in the youngest regime of this plot. And this is due to the latest contribution to the chemical enrichment of the galaxy from AGB stars. And in the oldest part, we have more or less a flat trend. But as I said at the beginning of this talk, so we need to take into account the spatial distribution of these stars. So here we can see the histogram of the so the radii of these samples, and we can see these stars cover a large range in radii. In that case, we use the so-called guiding radius instead the galactocentric radius, because this radius can mitigate the effect of blurring. So it is one of the 2 effects of radial migration. So for the reason, we divided this sample of stars in 3 different pins of guiding radius. And here we have the example for TESS dataset. So in the inner region, we have almost flat trend. This is due to probably a more intense star formation history in the inner part of galaxy. where the AGB stars start to contribute early. In the other two bins, we model the trend using a broken line to model the two different slopes. So for the young and old stars. And here we can see this slope, in particular in the youngest part of the plot, becomes steeper and steeper, moving towards the outer region. And this is due to a different star formation history in the different part of the galactic disk. Finally, we can see the same plot, but for chemical clocks. So cerium over 4 different alpha elements, so oxygen, magnesium, silicon, and calcium in the 3 bins of guiding radii. And also in that case, we see the slope becomes steeper, moving towards the outer region. For this, and this is show the strong dependence of these elements on star formation history. Finally here, chemical clocks can help us to have a more insightful view of the galactic archaeology, and exploiting the precise chemical abundances from large spectroscopy surveys and stellar age. So these abundances ratios calibrated on stars with well-known ages. So in that case, open cluster, solar twins, or stars with a seismic age allows us to derive also age for a large sample of stars for which we don't know ages in other way. So when we use this stellar dating relation, we need to take into account the dependence of metallicity and also on the position of stars. And our future plan is to exploit the synergy between astroseismology and spectroscopy to investigate other chemical clocks in other large spectroscopy survey. So I finish here.
Thank you. Okay, so time for questions. I have one, while I don't see now, still hands open up. So in your last plot, when you show the different trends with galactocentric radius, so what do you conclude about the star formation history from these different slopes?
So we are still working about it, but we just say the star formation history in the inner part of the galactic disk is more intense than in the outer part of the galactic disk. Probably in the inner part, the contribution of AGB stars, that is the stars that produced, in particular, S-process elements, start to contribute early with respect to the outer disk. So actually, we are also compare these results with the galactic chemical evolution models, but for the moment I don't have any to show you because we are still working on about it.
Okay. More question? One from Franco.
I might have missed the point because again, I'm not an expert, so sorry in advance. But so from this plot, given the relation are so shallow, so suppose I measure C over alpha of minus 0.2. How can I get an age estimate?
That's from this plot, I know it's difficult because here we have a huge scatter. So
Yeah, I would say the relation is very shallow and very scattered. So I missed how I can use.
So in that case, we have actually there is for the cerium. So for the other elements, it's easier. For the other chemical clocks, sorry. For example, here is more elegant.
Yeah.
But cerium actually there are some problem with these elements because, for example, in apogee they measure just weak lines of these elements, and then for the reason we have a huge scatter in the abundances. So it's not the best S-process element to use as a chemical clock. So we are just investigating these elements because there is a new one for apogee, because just in the latest data release of apogee, they give us a S-process element. So yeah, our conclusion about cerium is, yeah, we can see some trend, but they are not too steep to use as a chemical, so to use to infer ages for other stars.
Okay, Carlo, then there is another question from Angela, maybe from the online, already she.
Yes, I don't know if I'm just asking again something that Franco asked, because I didn't hear him very well, but while in this plot, the relation are very well, are steep for large ages, with cerium after an age of 6-8 gigayear, then the relation are flat.
I know. We are still working on it. I don't have a stronger answer for you, Angela. Yeah.
So it may be that cerium is not measured very, very well by apogee, especially
maybe,
for the oldest star.
Maybe, yeah, it could be.
Do you plan to do the same thing for instance, for Gala?
So this is the second step, because for Kepler, for example, we have just data from apogee. So
yes, of course, K2 and TESS.
And also TESS. So we don't have data from Gala or Gaia ISO. For K2, we have data from Gala and few data from Gaia ISO.
Sure. Okay, thanks.
Carlo? Maybe you want to get closer to the microphone, because I see that.
In one of your plots, you were referring to thin disk and thick disk stars. Can you show it again? So the question is, because I didn't get from the plot, if you are actually, yes. Are you actually distinguishing thin disk and thick disk stars here, or you're just saying that you expect
the thick disk? So okay, so if we talk about the chemical thin and thick disk, so the thick disk is these stars, and the thin disk are these stars. Maybe from this plot is easier to see the difference. It's small, but it's quite evident.
But you are not using information about
kinematics
or
that case, no.
distribution.
No, in that case, no.
Thanks.
Okay, Marco Palla.
No, actually, I have the same question about if you use the chemical or the kinematical distinction for thick and thin disk, but you just use it. You just answer, so it's fine.
Yeah. Maybe it's better to use the low alpha sequence and high alpha sequence instead of thin and thick disk.
Yeah, thank you. Anyway.
Yeah.
Okay, more questions from the public, from home? No? If not, let's thank again Giada. Bye-bye.
Bye.